I would like to thank you, our audience, for attending this seminar. Today we have very interesting lecture. Our distinguished lecturer is Professor Carlos Merile. Let me give some background on Carlos. He obtained his PhD in physics at the Universidad Nacional de Córdoba, Argentina, where his doctoral studies focused on the use of nuclear quadrupole resonance to probe structural and dynamical disorder in organic crystals. After graduating in 2000, he joined the group of Professor Alexander Pines at the University of California, Berkeley, to work on the physics and applications of nuclear magnetic resonance. In 2004, Carlos joined the Department of Physics at City College of New York, where he is now Martin and Michelle Cohen Professor of Physics. His research focuses on the combined use of optical microscopy and magnetic resonance methods to investigate the properties of quantum emitters in solid-state hosts for applications in quantum information processing and nanoscale sensing. Carlos has received several distinctions, including an election as an Optica Fellow in 2023. Carlos, the stage is yours.
Thank you. Thank you very much, Olga and Marco, for this opportunity. It's great to be here. And actually, I'm happy that unlike last time, which was a couple of years ago, the situation where I was actually presenting from a hospital because my wife had an accident that same day, the situation today is less dramatic. So hopefully everything is going to be more quiet and it's going to run smoothly. And as you can see from the title in the presentation, we're going to be talking about the use of color centers and in particular NV centers in diamond to investigate the dynamics of confined fluids. And more specifically, we're going to be focusing on water. Now, my name is on this first slide, but it shouldn't, because in reality, this is very much a collective effort. Here I've listed the names and I've included the photos of the real heroes, if you will, here, because they are the ones who carried out the hard work. And so I wanted to highlight that right on, because I think that in this particular case, unlike in some other cases, this is very much a interdisciplinary work that was only made possible by bringing together people with different expertise. So I'm going to try to highlight these different contributions as the presentation progresses. Here's an outline of what I plan to talk about today. I'm going to start with a quick background. I'm going to make some comments specifically on the different methods that people use for probing confined liquids, and in particular confined water, sort of to provide a kind of framework. And I'm going to also say a few words about relevant recent work, very much related to our discussion. And then I'm going to jump right on to the key results. I'm going to start talking about the fabrication and then monitoring of confined water via NV centers. I'm going to also present some results that reproduce, or try at least to reproduce, the observed dynamics via molecular dynamic simulations. We're going to see that there's a conflict between the results that, or the interpretation that we make out of the experiments that tell us the diffusion of these confined water molecules is super slow, with the conclusions that we draw from our molecular dynamic simulations that tell us if we put in pure water in these channels that we produced, the diffusion should be very much as in a bulk system. And then we're going to try to reconcile these two different conclusions by bringing in the role of charges. And we're going to show through molecular dynamics some kind of modeling in reality, because it's not strictly pure molecular dynamics, but it's combined with some model. And some clues that we these charges, these surface charges that we generate via optical excitation most likely play an important role in these slow water dynamics that we observe. Okay, so I don't think I need to spend much time motivating the study. The field of nanofluidics is already a well-established one. There's been, over the last decades, huge progress. And the driving force in these studies is essentially the fact that there's unique phenomena that take place at the nanoscale that simply you cannot see if you're limited to studying bulk systems. And among these different phenomena, you find singular rheology processes that take place. You see effects, strong effects on the ion transport. In particular, the selectivity of ion transport is one such aspect that, by the way, is central to, for example, the functioning of a cell. You even see modified stochastic fluctuations when confined sufficiently to sufficiently small volumes that ultimately alter the outcome of a chemical reaction. Now, the selection of water from among other possible fluids is sort of obvious, because water plays, as you most likely know, plays a key role in so many different processes that range from geophysics to biological activity to catalysis. Now, studying these confined fluids and water in particular is not at all simple. I do not intend to give you a comprehensive list of techniques that have been used for studying confined water. These involve X-ray, neutron scattering, etc. But rather, I wanted to highlight just a few examples to give you a sense and to contrast also the approach that we will be pursuing as opposed to what's been done before. So this first example relates to the use of atomic force microscopy. And in this case, it's been used for probing the a relation that exists between viscosity and wettability in water in particular. This is one example. There are many others. In particular, I can point you to studies where they use atomic force microscopy to even look at the layering of molecular of water molecules. And that is in particular an aspect that our molecular dynamic simulations are going to expose, and we're going to get back to this point as we progress in the talk. Now, the use of atomic force microscopy is very useful, but is not so useful when you're interested, for example, in probing dynamical processes, because the dynamical response or the dynamical range of atomic force microscopy is not so great. Also, you are limited when, as in the particular case that we'll study today, the water that you are trying to probe is confined in 3 dimensions. And so you don't have direct access to the water that you're trying to study. Now, one example of this situation is this paper here by Gaim and our collaborator, Boyarada, They used a structure that is somewhat similar to what we used here. I'm going to get back to the details later on. But in particular, they combined atomic force microscopy and then a capacitive technique to probe the dielectric constant of confined water molecules. In this case, the confinement was taking place in nanoscale channels that were created by 2D materials. And this is, as I said, something that is a sort of framework that, that we reproduce today. So I'll get back to these details in a second. Now, the use of NV centers for probing confined fluids, and in particular water, was proposed theoretically by the Plenio group in this paper a couple of years back. In this particular paper, they were interested in understanding or trying to expose through NV centers phase transitions in water, but many of the ideas that they talked about are ideas that we'll get back to today. Now, to the extent of my knowledge, I might be wrong, but to the extent of my knowledge, there's been no studies of measurements of water. In particular, we have to emphasize unpolarized water using NV centers before. But it so happens that in December last year, there were these two papers that came out simultaneously with ours. The first one from this group in China that used shallow NV centers, as in our case, to study the dynamics of, and hopefully you can see the cursor, right? When I move it. I didn't check that before, but hopefully that's the case.
Yeah, we can see. We can see.
Okay, thanks. So, so in this case, they use shallow NV centers to probe water that's being absorbed on the diamond surface and then capped with a 2D material, again, an HBN flake. They study this for different for different exposure times, and those exposure times correlate with the thickness of the adsorbed layer, and so they can extract a relation between the diffusivity of these, or the self-diffusivity of these water molecules, and the thickness of the layer they probe. There's also this work, again, simultaneous work that came out from Zhangfeng Du's group, also in China. In this case, they were using shallow NV centers to probe adsorbed water that came from exposure in a chamber, to separate this adsorbed water from water that, or protons that came out from some other sources. They resorted to deuterated water, and they made observations that in many ways, even though there's no explicit confinement here other than the surface of the diamond itself, but they reached conclusions that are very much related to the ones that we'll be discussing today. So I'm going to get back to this and probably the other paper too later in the presentation. So here is the structure that we used. This is a, this is schematic, and you can see these strips of hexagonal boron nitride. They have a height of about 5 nanometers, 5.6 nanometers exactly. They sit on diamond, and they've been capped with a very thick layer of hexagonal boron nitride too. This is sufficiently thick so that the capping layer doesn't sag or bloat when we essentially put in water in those channels. And I'm going to explain in a second how we do that. Now, before that, I want to highlight the work of Ankit and Radha here fabricating this. This was essentially the starting point of our journey. This is an atomic force microscopy image of the strips of HBN that they produced. Here you can see the height and the periodicity of these channels. The process is pretty convoluted. I really don't want to embarrass myself trying to describe this in detail because this is definitely an area that is not within my expertise. But roughly, this gives you an idea. So you start with this flake on silicon dioxide that you pattern with combining electron beam lithography and dry etching. And then you create these strips, and then you cap them with this hexagonal boron nitride capping layer. Shown here, down here, you can see the smaller flake that you started with that now has been patterned, but also now covered with this capping layer. What you do next is you resort to PMMA and you use it as a membrane, and that membrane you essentially use to transfer the structure that's been created onto the diamond surface. And this is how it looks already after the transfer on diamond. Once on diamond, what you do is you again resort to beam lithography and dry etching to open up these two windows that you see here in gray. Here at the center, you essentially have the channel area. And the idea is that you're going to resort to these openings to fill up those channels. So you're going to expose the structure to water vapor, and then water molecules are going to, after sufficient time, which typically takes, the whole operation takes about a day or so, we fill those channels with water molecules for further study. So here's again another image, and what I wanted to highlight here is the advantages of these architecture for confining water. First of all, it's something important, perhaps, is the fact that once the water gets inside these channels, it stays there for sufficiently long for us to do all kinds of experiments. The time during which we can work without worrying about the water being still there is about 2 weeks or so. This has the advantage that the fact that actually we can fill and then empty those channels has the big advantage that we can make sure that what we are looking at is water molecules and not something else. And these, for those of you who are not familiar with magnetic resonance, you have to realize that protons are pretty much everywhere. In every organic molecule, you're going to see protons. And so protons can be introduced accidentally during during engineering the structure at any stage. And so you actually want to make absolutely sure that when you talk about certain dynamics, what you are looking at is water. So this structure is something that allows us to do that unambiguously. And then the fact that we can reuse that same structure multiple times gives us the option to study water in the same structure, but under varying external conditions. So we're going to get back to these ideas later on, but I wanted to highlight this early in the presentation. Now, as you can imagine, exposing this to water vapor in a controlled manner cannot be done in an open environment. And so what we did was we prepared the whole structure. We inserted the whole structure in a microfluidic device. This microfluidic device has these two inlets here that I've sort of indicated. The diamond sits here, and then you have yes, as I said, there's some other details, but we don't have to worry about that for now. And there's these are the two inlets, and here we can insert either fluidic water, liquid water, or we can circulate a water-saturated gas. Typically, we use argon, but we can use others. This is a schematic of how the overall structure looks like. This is our microfluidic device. This is the diamond that gets enclosed in this chamber, and this allows us to control the environment and all the conditions during the channel filling. This is how roughly a finished board looks like. And one aspect that will be important here is this insert photo that shows the little loop, the little coil that we use for microwave manipulation. This will be important in controlling the NVs and extracting the relevant signal. Now, I'm pretty sure that most of you in the audience are super familiar with NV centers, so I won't bore you with information that you already know. But just in case there's someone, that is participating for the first time in this series, just a few words. This is the geometry that we have. So we're using a very special diamond as well. So in particular, this is a diamond that has been overgrown with a carbon-free layer, about 100 nanometers thick or more. I don't remember exactly how thick, but it's quite thick. Then this being implanted with nitrogen-15 to create a layer that is about 8 nanometers deep. And here comes the structure that surrounds the water molecules. And so what we're going to be using is confocal microscopy to probe the NVs, and in particular do NV magnetometry, and sense, therefore, the field, the magnetic field created by the protons in the water molecules. Now, here on your right, you can see a schematic of the energy diagram for the NV. This is the ground state, which is a triplet. The excited state is also a triplet. And as you probably know, you use green light to initialize the NV center because there's a spin-selective intersystem crossing onto a singlet manifold that is going to lead to preferential population of the ms equals 0 state in here. And that very same mechanism is the one that is going to be used for sensing what the spin state is after spin manipulation. Now, the manipulation of the NV spin takes place on this ground state manifold. We typically work with a magnetic field of about 450 Gauss or so. We focus on this particular transition. So under 450 Gauss, the plus minus one states split. They are degenerate otherwise, but they split with this magnetic field. And then we focus on the transition that goes between 0 and -1. And then I also want to highlight the fact that because you have nitrogen-15 and not nitrogen-14, the difference between the two is that nitrogen-14 is a natural isotope, but it's 99% abundant. If you instead use nitrogen-15, you sort of guarantee that you are looking at NV centers that are the ones that you've engineered. And these nitrogen-15 happens to be an isotope with nuclear spin equal to 1/2. And so that essentially splits the plus and -1 states into 2, not 3 sublevels. And so as a result, if we're looking at the 0-1 manifold, we're going to see 2 and not 3 transitions. So this is what happens here. If we implement standard ODMR, optically detected magnetic resonance protocols, in the 0-1 transition, this is the sort of spectrum that we see. One line corresponds to the 0-1 transition, but connecting the plus 1/2 hyperfine states. The other one connects the -1/2 hyperfine states. And the reason why one is much bigger than the other one is because close to 500 Gauss, 512 Gauss exactly, you will have processes, I won't get into that, but you will have processes that are also induced by optical excitation that lead to nuclear spin hyperpolarization. And so preferentially, you will find this state as opposed to these other states. And this is actually advantageous for us because essentially it allows us to narrow the line and with that improve the sensitivity of our experiments. Now, under those conditions, what we can do, just as for starters, to give you a sense of what we are dealing with here, is a characterization of these ODMR that comes from the NVs as a function of the position in the channel structure that we've created. So if we move along this line that goes parallel to these channels, we get and record ODMR spectra as we move along. We get this series in here that you can see on the right, on the far right. And so something that you notice is two things. First, there's a shift, a gradual shift as I move from 2 to 2 prime here, the one window to the other. And then that there's a dimming of the fluorescence and a reduction of the contrast. Now, the shift we can simply ignore because that comes that results from the fact that we have field inhomogeneity. We're creating a field with a local source, and this leads to inhomogeneity and a shift in the resonance frequency. So that we can ignore. But this dimming is important because obviously it affects the sensitivity of these experiments. The reasons, quite frankly, this happens are unclear at this moment, but I have the strong suspicion that this comes from a change in the charge state of the NV centers induced by either the HVN structure or some process in the fabrication process during fabrication that slightly alters the surface in a way that changes the charge state of the NV. And this change in the charge state of the NV is something that is going to be recurrent. So I wanted to show it early on because we already see when we just go to the NV characterization that here charge is playing an important role. Now, if we want to do nuclear magnetic resonance of the protons in the water molecules that we've trapped, one technique to follow is this one that I'm pretty sure most of you are familiar with. The idea here is that you apply a train of pulses whose spacing is chosen so that you can make it effectively resonant with the Larmor frequency of the nuclear spins that you are trying to probe. And so the result, as you change these, as you change the spacings between these pulses, is shown here, either before or after filling the channels with water. And in the latter case is when you can see a clear dip that indicates the presence of these water molecules. Now, you can argue that over here, there's also a signal, even if smaller, and that is actually the simple result of the fact that this is not the very first measurement. As I explained before, we've gone through multiple cycles of filling the channels and then doing measurements and then letting the channels evaporate. And so these can be seen as a leftover prior to refilling this channel. So this is more likely the reason why we already see some background signal here. Now, importantly, you can see this signal only in the channel section of the structure right here, as presented in this plot. If you actually move your sensing to NVs that are in the windows, you essentially see no signal. So this is another confirmation that tells us, okay, so what we are seeing is water molecules and not something else. Now, when I said this is the first sensing of water, and I use the word unpolarized water, I essentially refer to the fact that these techniques work with what we call spin noise. Essentially, this is detecting the statistical polarization that protons in this system take. And this actually has a very important consequence. This being the fact that if we detect this unpolarized water, if we detect this statistically polarized water, what's going to happen is that the signals that we get are going to become immediately sensitive to diffusion. So if a molecule that has, if proton spin that has some phase is initially sensed in this volume, the NV probing the effect is right here, and then leaves during the sensing time, leaves this sensing volume, then and is replaced by another one that comes in with a different phase, that's going to cause decoherence. And so that's the reason why looking at the coherence of the NMR signals that come out from these from this setting is going to provide us crucial information about the diffusivity of these molecules in this structure. So there are different techniques to probe that. One technique that we introduced several years ago and that now we can apply here is this one that is a variant of the NMR protocol that we discussed before. The main difference being here, the fact that we leave some evolution interval between the two trains of pulses that we apply, each of them resonant with the nuclear spin of these protons that we're interested in. And so this is the signal that we can collect from such a measurement. If we do a Fourier transform of this signal, what we get is clearly a resonance at 191 megahertz, which happens to be the Larmor frequency for protons in the applied magnetic field. Now, you can see that already this Fourier transform not only has this central peak, but it also shows some weird shape. I'm going to postpone the discussion of this shape for later, but I simply wanted to highlight that this is an important issue. Now, out of this, if for a moment we ignore these aspects and we just focus on the envelope that describes these correlation signal, the way we refer to it, we already start learning some important information. So, for example, if I use a damped sinusoidal, exponentially damped, to describe this signal, what we see is that if I try to match the early behavior, then the signal decays very quickly, too quickly. If you ask, well, can I use multiple exponentials to fit this decay? The answer is definitely yes. But it so happens that in the not so long ago, the Retzker and Telesco's groups introduced and discussed the behavior of, or the sort of envelope shape that would come out from a measurement like this. Long story short, the key issue here is that the surface of the diamond interface itself creates restrictions on the way molecules can detect. And these restrictions translate in a special shape that the envelope is going to take. And so this is a complicated formula. I simply list it here for completeness, not my intention for you to understand or follow this formula. But I'm reproducing here with this faint trace some fit that we do to the signal that we have. And this would correspond to a characteristic decay time of 2 microseconds. Now here we still see that the agreement is much better than using an exponential, but still the agreement is not great. The problem being that if I try to match again what happens at early times, then I underestimate the signal that I'm going to get at longer times. If I do the opposite, if I try to fit the behavior at long times, then I overestimate what's going to happen here at short times. And so one way to get some kind of agreement, better agreement, is to combine contributions now that have different characteristic times. In here, I'm referring to a contribution that I label with an F indicating a fast decay, and then with an S indicating a slow decay. In these weights here are simply give me an idea of their contributions, relative contributions. And here you don't have to misinterpret these as a proof of anything. It doesn't prove anything, but it just suggests that there's heterogeneity in the way molecules diffuse in here. Whether there are 2 layers or more layers, it's unclear. This is obviously not the way to see that, but it's simply the takeaway message in here is that the behavior is more complex and more likely layered. The diffusion coefficients that we get out of these analyses is also another important aspect that I wanted to highlight, because even if we were to look at the fast diffusion coefficient that we extract through this formula down here, we get this value that is about 2 orders of magnitude lower than the value that you'd expect for bulk water. And the difference is even worse if we were to look at the slow component in here. So we have already 3 orders of magnitude less diffusivity if we concentrate on the long-term behavior. Now, we actually try to make sense of our observations. And for that, we resorted to molecular dynamic simulations. Again, this is an area that exceeds my expertise, but I'm going to try to give you the gist of it, of what was done. In the model, we essentially generated a structure, a diamond structure that was surface terminated in different ways. In this particular picture, what we have is an OH termination, but we've looked at oxygen termination, hydrogen termination, a mixture of the two, etc. And I'm going to get back to that in a second. There's also a single layer of HBN on the other side, separated by 5.6 nanometers, trying to match exactly the dimensions of the channels that we were looking at. And what you see in this plot in here is a snapshot of the water molecules inside filling that channel. What you may notice if you go close to the diamond surface is some type of layering. This becomes more apparent when we reconstruct the density as a function of distance to the surface. Z is the axis perpendicular to the surface. And this layering appears here as a modulation of the water density close to the diamond surface and close to the hexagonal boron nitride surface. Now, with this layering, one might first think that there's natural order and therefore a slower diffusion of water molecules as they approach these surfaces. But this is actually not the case, because if we calculate the mean square displacement for these molecules, even in these layers selectively for layer 1, 2, or 3, what we see is we can extract out of this slope a diffusivity that is very much comparable to what we get for bulk systems. And so really the presence of the surface, if we consider just pure water, is not something that on its own is going to explain why we see the slow diffusion that we see. Okay. At this point, we are at a crossroad. We spent some time trying to figure out how to make sense of this agreement, if you will. And it so happens that not long ago, very much almost in simultaneous with the experiments that we were doing with the channels, we were also looking at we were doing other experiments where we were studying, in particular, the influence of charge dynamics under optical excitation. And so what I'm going to do here is, because this is a key aspect of the discussion, and it's a non-trivial assumption that we're going to make, I wanted to open a parenthesis here. It's going to be a rather long parenthesis. Hopefully it'll work and you won't lose track of what I'm trying to present here. But I'm opening a parenthesis to make a summary of some observations that point to the importance of the charges being generated under optical excitation. And in that context, one first thing that I have to say is that, for those unfamiliar with it, is the fact that the NV, when we talk about the NV in general, it's always about the negatively charged NV. But the NV comes in two flavors, at least. It can be negatively charged or neutral. And the difference is, if we think of it in the crudest possible way, as a two-level system, is a separation between these two-level systems. In one case, in the neutral case, is greater than in the other case. But what happens is that if, for example, we were to use green light and start with NV minus, if the green light is sufficiently strong, what's going to happen is that a second photon is going to arrive at the time the system is still excited. And so what's going to happen into the conduction band, and we're going to end up with a neutral NV. So green light gives us a process of transformation from NV minus to NV zero. It so happens too that if we are already in NV zero, green light is sufficiently strong to excite NV zero and inject an electron from the valence band. And the result is that there's a hole now injected into the valence band and a transformation from NV zero to NV minus. And so under green excitation, essentially transformation back and forth, and with every transformation we're exciting and we're injecting an electron and a hole. So neutrally, we don't create a net charge, but we are creating lots of carriers. And this is actually something that we demonstrated experimentally for a system very much similar to the one that we are looking at today, because in this case, what we have is a bunch of diamond membranes that have been implanted with NV centers, have been stacked on each other. They are separated by some micron distance, and using a microfluidic device very much similar to the one that I presented before, we flow water through this structure. And then we have two electrodes on the sides, and we apply voltage. Importantly, these electrodes do not make physical contact with diamond. They are also in contact with the water, but not with the diamond surface in any way. And what we see is that by doing that, when we look at the current that circulates through that circuit that now we've created, we find a clear signal. I won't spend time into the details of how we get to that signal. We can discuss that after the presentation is over. But for brevity, I want to highlight there's a clear signal, a current signal that we measure under optical excitation. And this signal grows with the bias that we apply. And we have seen that this is very much dependent on the surface that we use, that if we, for example, go from diamond to glass, we'll see no signal. If we are with diamond, but we don't apply green light, or we apply light of different powers, what we see is an increase of the signal that makes full sense in here. Another aspect also for completeness that I want to highlight is that this emission is very much sensitive on the wavelength that we use. If we use green light, we'll have a very strong signal. If we use red light or reddish, I'd say, light, it'll become less apparent. If we go to the blue, we'll see a gigantic signal. And interpreting the different sources, there is, a discussion on its own. I won't get there either for brevity as well, but I want to say that on the surface, besides the NVs, you have other traps, other systems that can be also excited and charge cycled that serve as sources of charge. In no way were the first ones to report this. These are papers, for example, relatively recent papers that talk about these dynamics, although under different conditions, in particular, often going towards the blue, where the signal is stronger. In our case, we concentrated on the green because, of course, we have the NV centers, and we wanted to see if the NV centers themselves were producing also carriers that some of which flow into the liquid in contact with the surface. And what we found is that the behavior with the laser power is rather linear, and this wasn't great because as we know, as I explained before, this charge generation is a two-photon process, and so we'd expect something quadratic. However, if we were to replace the protocol here, modify it slightly, now transitioning from a CW laser that is being switched on and off to a pulse laser, we essentially increased the applied power quite substantially. And in that case, what we find is that the process does become quadratic, not proving, but strongly suggesting that the NV centers do play a role in these charges that we see being injected under green excitation. So with that, I want to close these big parentheses that I opened, and I want to go back to the big question that our experiments and simulations posed for us, which is, in one case, we get diffusion constant that is very slow, 3 orders of magnitude slower than in bulk. In the other case, we get a bulk-like behavior. But now we know that under this green excitation that we apply virtually over extended periods of times, we're talking about experiments, each of them lasting for at least a day, oftentimes more. We are definitely generating lots of charges. Those charges have to land somewhere. And so we started thinking, well, how about, what is the effect that these charges may generate on the dynamics of the water molecules that we trap? Now, if you think about it, it's not simple at all to model a system like this. When you inject electrons, for example, in water, which is the more likely scenario for reasons I can explain later, electrons are not an inert species, right? They'll react, and therefore there's very complicated chemistry that takes place in that water. That's extremely difficult to model. Maybe you can get a sense via quantum mechanical calculations, but then at the molecular dynamics, it just becomes impossible. And so you have to make, a trade-off. Some would say a crude trade-off. This is what we did. We assumed that rather than having electrons injected, we had some ion, and in particular, we went for the simplest that we can think of, and that's a fluorine ion, negatively charged fluorine ion. We introduce these fluorine ions in the water, and then to make the overall system neutral, we distributed positively charged ions on the diamond side. And there are physical reasons that make that choice reasonable. I can get to that later. But we started with that system. The ions were uniformly distributed throughout the channel, and we let the system evolve. And soon enough, what you end up is an equilibrium distribution where if you go back to the density, and perhaps it's not as clear as I'd like, but you may notice in here that if you are plotting, say, the fluorine ion density, you will see an oscillation that alternates. It's 180 degrees phase shifted with the density of water molecules, essentially meaning that the ions just organize and form layers close to the positively charged diamond surface. And then in the pockets between these layers, water molecules also organize. And so this is what we see when we look at, when we take screenshots at these different layers. And these are the different water molecule layers that we find at different distances. Now, the interesting aspect is that when we now recalculate the molecular, the mean square displacement for these different layers, you already see a big effect. When you go far, say to layer 3, the diffusion is fast. But when you go close to the first layer or the second layer, you already see that the diffusivity has been altered quite dramatically. And within the measurement or the sort of observation window of molecular dynamics, we see essentially no displacement, indicating that there's some kind of order that is taking place. And this observation relates very much to predictions from also molecular dynamics of pure water in the presence of externally applied electric fields. Remember, by the way, these are all Coulombic interactions, so there's no chemistry in here involved. As I was saying, there's preceding density functional theory calculations that show that the presence of very strong electric fields will slow down the water dynamics. It was just assumed that the fields in there were just too strong for a realistic electrode to generate those fields. But a distribution like this seems to be doing the job. So again, I'm not doing justice to the work. This is a very extensive work that was done by Capilla and Nicolas and Gustavo. They tried, we've investigated different surface terminations. We've looked at different spatial distributions of the positive charge. We've looked at varying numbers of solvated ions. We've looked at other ions. We've looked at artificial ions that had different sizes. In all cases, we found very consistent results, indicating that these observations that I'm reporting here are very robust to all these parameters. So it's not something that came out accidentally from the conditions that we chose to simulate in this case. Now, NMR is more likely not the technique that you use to demonstrate or to prove or disprove an idea like this. Nonetheless, I wanted to highlight, and with this I will end, I wanted to highlight some aspects, some clues that we gather out of the observations that we've made that somehow point along very much these lines of thought. And to get started, let me go back to the spectrum that I had highlighted before. As you remember, maybe this is the Fourier transform of one of the correlation signals that we saw. And I highlighted the asymmetric shape that we get out of that Fourier transform. Now, here is the physical picture that we imagine. We have our NVs in here, we have the water, but then there's also these negative ions in here, and then positive ions somewhere here within the diamond side and close to the surface. Now, the idea is that when you have these solvated electrons, at least in this particular drawing, what you could imagine is that now, if everything is sufficiently mobile, there's going to be hyperfine interactions between these electron spins and the nuclear spins, the protons in the water molecules. And these hyperfine interactions are going to alter the spectrum, the magnetic resonance spectrum of these protons in a non-trivial way if these interactions are sufficiently strong. So here, this energy diagram sort of summarizes these expected changes in the presence of hyperfine interactions. Long story short, we can imagine different layers with different decreasing hyperfine interactions. Importantly, they are going to be shifted to higher frequencies, and they are going to then create a sort of asymmetry when compared to the main peak that presumably will come from water molecules that are not exposed to these local surface charges. And so we can reproduce reasonably well the spectrum with that simple assumption. Is that a proof? In no way, but it's, again, something that suggests we are not so far off. Another indication comes already with from the NV microscopy that we do. If we look at the microscopy immediately after filling the channels, and this is an area close to the area that we've been investigating in the channel section here, you see a distribution of brightness that alters quite substantially if we look at it, just an hour later, and this reveals a change in the charge state of the NV center. So what's going on here in terms of charges is not at all trivial. Now, after an hour or so, things stabilize. This is not changing any longer. So if you were to do microscopy here, you will exactly see the very same image time and time again. But if you do over a long period of time NV-NMR measurements, things happen. They are not fully reproducible, but I'll give you a sense with one example. So in this particular case, on day one, we start with this ODMR peak that very much goes along the lines of what I already presented. If we were to look at it 7 days later, what we find is that now the line is much narrower. In this case, 19 kilohertz. In reality, this is not the real line width. This is more likely broadened by convolution. If we look at correlation signal in here, what we find is a signal that it's very long-lived. And if you notice in here, I'm not starting from 0. We're starting from 20 microseconds already, and the signal persists all the way to 30-something microseconds as well. So that already, with no clear decay. So this already tells us that the dynamics has been altered to the point that now the diffusion coefficient is almost 4 orders of magnitude different or slower than the diffusion in bulk. And then if we wait 7 more days, what we find is that now the line width has become broadened again. But unlike, one could imagine, well, perhaps the diffusion now becomes high again. But we find these shoulders in here that again can be interpreted in the context of these hyperfine shifts that I was talking about, except that in this case it's more selective. It means that there's one type of hyperfine coupling rather than a collection of couplings. So the last comment I wanted to make is that this observation very much fits along the lines of what was reported in one of the papers that I highlighted early on in the presentation. In this case, they talk about paramagnetic shielding, which is different, if you will, to what we are discussing here in terms of the formalism. But the physical picture, as you can see from the drawings, is not so different from what we have in mind. So this is simply to see that coming from different directions, you doing related but not identical experiments, we get to conclusions that are more or less in agreement, I'd say. So with that, I'm going to conclude. I think very quickly, we demonstrated the trapping and detection of water molecules in nanochannels. We found that the dynamics is much slower than in a bulk, up to 4 orders of magnitude. We tried to simulate the effect with molecular dynamics. We found that if we stick to pure water, we cannot. However, if we look at the at new simulations that now include charges, we can come up with results that are consistent with our observations, at least qualitatively consistent. We also see experimental signs that these ideas are on the right track. I'd say that's as much as I'd say. And then, of course, looking forward, there's a bunch of experiments and ideas that we can test. These experiments have taken place at a fixed temperature. They've had a fixed geometry. They've had a fixed surface termination, and all of the above we can change in future experiments. We can even insert ions in these channels, where there's been very, very interesting phenomenology that's been observed in water containing ions, real ions, memory effects that we may be able to probe with the technique that we discussed today. And so with that, I want once again to highlight the work from people in my group and my close collaborators here on the sites. They've been central to this, as I said early on, and all of you for your attention. Thank you.
Carlos, thank you very much for extremely interesting talk. Definitely diamond is very complicated system and kind of peeling off layer after layer in understanding the phenomena you observed. It's very interesting to follow your presentation. So we are open for questions. Please unmute yourself and feel free to ask your questions. Maybe I will start so far with one of my questions. I wanted to ask, how do you control water purity? There can be oxygen dissolved in water in general, so you do some kind of argon bubbling or some other water preparation to get rid of dissolved oxygen, which is paramagnetic and can impact definitely dynamics of protons in water and readings of NV centers.
Look, if it was me, I would just use tap water. But, luckily for us, these decisions I don't make. I have chemists in the group who have actually made those decisions for me. Daniela being one, Abe Walcott being another one. They made every effort in deionizing water and purifying water on top of the pure water that we got access to. So we are pretty sure that the water that we put in there has the highest standards of purity.
As in also choice of HBN flakes. Was it just for structural convenience of having something with very precise thickness, or there is some additional motivations?
Yeah, so in general, I mean, these same structures can be made out of graphene, for example, and you would have the same level of control. The reason why we went to hexagonal boron nitride is that, at least for graphene, it's known that the presence of graphene close to the surface quenches the NV fluorescence. And this happens because there's a fret process between the NV and the graphene, which is a metal and has a continuum. So essentially, you have an energy transfer process there that is quite efficient and quenches the NV fluorescence. And that will create problems in the sensitivity of detection. So this we knew because this was already measured by, for example, the Rachter group. So we decided to go with graphene, where you have the same level of control, and in principle, you would have a more inert response because these fret processes wouldn't necessarily, I mean, at least in principle, we wouldn't imagine they are there. Nonetheless, as I showed, we do have quenching of the fluorescence, and quite frankly, we don't understand where that comes from. So it seems that HBN is not so inert as we might expect. Other people have looked at HBN. They haven't really complained much about it. But typically, when you do experiments with HBN, you would normally work with very thin HBN, meaning that the effect that they have, if it's, I wouldn't say fret, but fret-like process, it will be scaled down because there's not enough material. If now instead we have a 70 nanometer thick capping layer, the process, whatever effect we're causing might be more substantial. But in short, I don't have a concrete answer as to why the fluorescence dims a bit.
Hi, Carlos, I have a question.
Hey, Adrian.
How are you? Thank you very much for the nice talk. I know in here you are focused on polarized water, and then, I mean, any plans to work on pre-polarized water and then maybe to increase the signal-to-noise ratio? And the second question related to, you are detecting statistical polarization, and maybe when you go to thermal polarization detection, maybe you can have narrower lines and maybe you can have more feature about the hyperfine coupling inside water.
Yeah, so starting with the second part of your question, I mean, thermal polarization is conceivable, but it's really very difficult to attain to a level that would make, your signal to noise ratio go up. I mean, you would need to have virtually infinite fields for that to happen. Even a 10 Tesla magnet will give you something in the order of 10 to the minus 5 proton polarization. So 10 to the minus 4 maybe. So it's really very very difficult. If you do the math and the transition from going from detecting thermal polarization, or actually polarized protons as opposed to stochastically polarized protons at the nanoscale, you would actually need to have a very high level of polarization to transition to a regime where detecting polarization becomes favorable. Now that is possible, and people have done it with either pre-polarization or with hyperpolarization. And as I said, in that case, you may become perhaps, I'm not sure, you may become a little bit more sensitive, but then of course you sacrifice your ability to detect diffusion, because in that case, looking at one NV that is within the detection volume and now is replaced by another one that has identical phase leads to no effect on the signal that you pick up. And that's essentially the reason why pre-polarized water was used in prior detections of water, not stochastically polarized, because every attempt failed in detecting stochastically polarized water because of the high diffusion that water has.
Okay, thanks.
Yes, I have one really quick question. I think it should be pretty easy, but like early on that I didn't quite understand. Early on in the talk, you were showing I guess the ODMR spectra of the, I guess, -1 that was split asymmetrically of the plus and minus 1. I noticed that your frequencies are like 1.675 approximately gigahertz as opposed to the standard 2.87. Is it like an excited state, or why is it so much lower than I'm used to seeing?
No. The big shift, it simply comes. I mean, in different runs, we have to oftentimes, things get misaligned. Things need to be tweaked over and over again. The system is, in a way, very much living, and so Roma and Daniela had to be very much on the system every day, and oftentimes, there will be a big temperature change, or the sample has to be, or the whole chip has to be taken away, and then, for experiments to continue, you need to realign and start all over. Every time you do that, the exact positioning of the magnetic field changes, of the magnet changes, and therefore the magnetic field changes. And so the big shift in the frequency, hundreds of kilohertz or something, comes simply from changes in the positioning of that permanent magnet nearby. What we are, I mean, we know, in every case, we know what the Larmor frequency is for protons, because we're also simultaneously doing NVODMR. And that gives us already, a measure for what the applied magnetic field is. So then we know where to expect the nuclear Larmor frequency, and we can compare,
Okay, cool.
Carlos, you mentioned that diamond surface is positively charged. And what is specifically surface chemistry on your diamond plate, and where conclusion on positive charge came from?
Yeah, so the diamond here is chemically terminated, which, the community has sort of agreed amounts to having a mixture of different types of termination: OH termination, O termination, hydrogen termination. A mixture of all three, and perhaps other types of termination, are possible. But on average, people refer to as OH terminated as equivalent to chemically terminated. That's what we have here. And that's the reason why, when we try to reproduce the observations from molecular dynamics, we needed to consider different types of surface termination. What was the other part of the?
Positive charge.
Oh, the positive charge. When you have this type of, so what happens is that when you have hydrogen termination, the valence band, so the band structure bends positively. So positively that the end of the conduction band typically goes to an energy that is higher than the energy corresponding to the free electron. So two things happen then. If you have holes, these holes are going to go towards the surface. That essentially translates into a preferential charge change of NV minus onto NV zero. And that is the reason why a hydrogen terminated diamond is, not good for sensing. So now what you try to do to improve the sensing, what the community has done, I mean, we've just followed recipes here where we have not participated on, contributed to that. But what the community has learned is that if you do this chemical termination, then you can somehow mitigate that band bending. You don't make it disappear entirely, but you reduce it. And so if that is the case, then what happens is that you are left with a higher concentration of NV minus that you can use for sensing. However, because the bending is not fully eliminated, if there are if there are holes around, these holes are going to accumulate on the on the diamond surface, forming. So in the extreme case, for example, when you have hydrogen termination, they end up the band bending goes above the Fermi level outside, or the chemical potential, and so you create a net population in there of what people refer to as a 2D whole gas that lives in there. So at that in that location on the surface, you normally accumulate positive charges, holes in particular. Now, if you excite the NV and ionize the NV, and the electron makes it to the surface, if you have hydrogen termination, or less so, but still so, if you have hydrogen, OH or chemical termination, the electron is having a negative affinity, meaning that it gains energy, the system gains energy if the electron now leaves the diamond and jumps into the solid. So that's into the liquid. So that's the reason why it's, the physical picture, we don't do statements. We cannot make any statements about the sign of the charges. That I want to make it clear. But at least from a conceptual point of view, and given this background, it's more reasonable to imagine that then electrons leave the diamond and get into the liquid, and then the positive charges stay on the diamond side of things. Hence the selection of the charge distribution that we made.
Thank you. Do we have more questions? It looks like no more questions, so we would like to thank Carlos again for very, very interesting presentation today.
Thank you, Carlos.
Thank you all.
Thank you. Bye.
Bye-bye now.
Thank you.